Alright, a few little updates on some things I did off stream here. So I created this new repo. It's just a README. It tracks all of the learning projects that I'm doing. And one of the things that I want to get around to, I started on this last year, which is the Stanford Parallel Computing course. I didn't realize like they issued a new fall 2025 version, so they've updated it, which is nice. It's this Kayvon guy who is a great lecturer. So I wonder if they actually updated the lectures. Probably not. Let's see. So that's the PDF slides. To the public this year, but videos in the prior version of course 23 are okay, so they only have the previous lecture videos, but they have updated slides and programming assignments and written assignments. So I look forward to diving back into this at some point. The Zig documentation for the language reference, that's something I wanted to get around to reading. I was inspired by Mitchell Hashimoto. He said that he read the Zig language when he was learning Zig. He just read the language reference, and that's something I've done for other languages. So I'm glad that there's people out there just reading the reference. So that's something that I want to do once I start diving into Zig. But yeah, today we're going to be doing more. Oh, the other thing I want to do is I set up a Codeburger account. I want to get all of my repos pushing to both GitHub and Codeburg, just to reduce my dependency on GitHub. And then I found this compiler's book. It's down towards the bottom of the books that I'm interested in reading. It's the Dragon book, but I guess when they published it, a newer updated version it's still the second edition, but it's a more updated version for the Indian market. They didn't put a dragon on it, which is sad, but it is the Dragon book basically. So that is something that I want to tackle at some point as well. So yeah, just some of the things I had open here. So let's go ahead and get out of that. Make sure it's up to date with GitHub. And then we have our K&R C book. So we are on structures. I'm gonna get my book out here and we'll start diving back into where we left off yesterday. All right. Yesterday I was just like, my mind was not in the place where I wanted to read any of this stuff. I was getting kind of like a little bit frustrated and bitter. Because I was reading this book and I'm just like, I'm not learning anything. It's so frustrating because a lot of this stuff I'm already very familiar with. But it's part of the process. I wanted to get this book read, and later on, the language reference, I'll be able to learn a lot from that. So let's just get through this. If we're in an area of the book that we're not learning a lot, we'll just get through it. You know, it's not the end of the world. Let's make it a little bit closer to the right screen size here. Okay, cool. Okay, so we got a main function, we got a bin search, a binary search, we got some forward declarations, we got a pound defined, max word. I forget what this program is intended to do, but we'll just read it and we'll figure out what it's intended to do. So we forward declare get word and bin search. Bin search is defined down here. Get word is not. Get word is where? Here. We're using that there. So get word takes in the max word and a buffer. So say while we can get a word, if the word is an alphabetical word, then we do this bin search thing, and then we iterate over n keys, which I don't know where n keys is defined at. Maybe that's from C type. Test.c, pound include C type. .h. And then if I go to definition on that and then search for N keys, nope. String and standard IO, and then I'll just say like N keys, because I don't see that defined anywhere. Is there a header that I'm missing here? Or are they just making shit up? It was used here as well. And keys. Where's it defined at? That's a little strange. But there's some number N keys, and we're going to range over those, and they're an array of some sort, and then we're going to add that to key tab. So key tab was defined previously over here. Well, let's start reading from this array of structures, because I've forgotten all about all of this. I think I was just very frustrated and just going through it and not really learning or keeping track of what I was reading. So consider writing a program that counts the occurrences of each C keyword. Okay, so that's it. Keywords. And so we have to have a collection of keywords to test membership against. We need an array of character strings to hold the names, an array of integers for the counts. One possibility is to use two parallel arrays, keyword and key count, as in keyword and key count. Yeah. But the very fact that the arrays are parallel suggests a different organization, an array of structures. Each keyword entry is a pair of this char star and the integer, and there is an array of pairs. The structure declaration like this, where you define the struct and then the array and keys, declare the structure type key as an array of key tab of structures of this type, and sets aside storage for them. Each array of the element is a structure. This could be also written. So this is basically the inverse of the structure of arrays. This is the array of structures, which has different properties from a cache lining performance perspective. So then we got our struct key. Yep, different definition. I would prefer this version personally. Since the structure key tab contains a constant set of names, it's easiest to make it an external variable and initialize it once and for all when it is defined. The structure initialization is analogous to earlier ones. The definition is followed by a list of initializers enclosed in braces. So we have struct key tab, and then we start initializing it. And yeah, just initialize it strings with zeros. Initializers are listed pairs corresponding to the structure members. It would be more precise to enclose initialize for each row of the structure in braces, such as this. That's what I would prefer. But the inner braces are not necessary when the initializers are simple variables or character strings, and when all are present. As usual, the number of entries in the array key tab will be computed if initializers are present and the array is empty. Left empty. The keyword counting program begins with the definition of key tab. The main routine reads input by repeatedly calling the function getWord that fetches one word at a time. Each word is looked up in key tab with a version of the binary search function that we wrote in chapter 3. Oh, so this is where I wouldn't use binary search. I would use a hash map. I mean, that's basically the data type that this is most natural for, key value pairs, where your access pattern is key lookup, and you want that O of 1 lookup. The binary search is log n lookup, I believe, and so it's just not the right data structure here. But they do it this way because it's a simpler data structure for C, because C doesn't have built-in hash maps. Okay. Each word is looked up in key tab with a version of the binary search function that we wrote in chapter 3. the list of keywords must be sorted in increasing order in the table. That's the other thing, is that the order has to be sorted when we initialize for the binary search to even work. So it's not an ideal solution here. Okay, so now we get into the actual program here. So we have that get word that we mentioned earlier, the binary search, which we implement down there. So the main program, we have this max word 100 char star. That's just the buffer size for reading the word. So we get our word, we say, hey, are you alpha? Word 0. So is the first character in alpha? If it is, then we're going to search. If it's not, then we can just move on to the next word, because the first character of any keyword has to be an alphanumeric. Has to be a printable letter, A through Z, uppercase or lowercase. All right, and then so we say, okay, you're alphabetical. So then we go into this if. So we say binary search, the word, the key table, and end keys, which is the length of the table, I believe. So key table is like the pointer to the first element of the table, and end keys would be like the number of elements in the table. And then that gives us back n. So n would probably be the value at the location where the bin is searched, or it might be the index. It's the index because they're using it to count. Yeah, so it's a bit weird to use n variable, because n is usually an indicator of the number, the value, the magnitude, whereas I would be more appropriate here because it's the index into the table. So a bit confusing in the variable naming. Usually n is like the variable used when you're doing a read or write. You'll assign to n, which is like the number of bytes. So in my mind, it's more of a value name, which would be what the index is, what the value of the index is. So if you had like a count here for char as a keyword, and it was 100, I would expect n to be 100, but they're returning the index, which makes total sense. It's just the variable name is a little weird. So they increment the actual count with that expression there. And then we go into for loop where we say, hey, we're going to iterate over all the keys. So it's a linear scan. The previous one was going over every word, doing a logarithmic search of the table, and then potentially incrementing it. And then when we're done with all that work, then we go through and do a linear scan of the table, and we say if the word count is greater than 0 for that entry, then we're going to basically just print out the count in the word. So pretty straightforward program. Bin search itself, so that takes in the word that we're searching the table for. And again, we can mod 2 equals 0 on the actual location in the table, because if I recall correctly, no, this is doing a struct. Okay, so we can't do that mod math. The initialization format kind of made me think we could, but okay, so we're not doing any of the mod 2 stuff. So we take in the pointer to the character word, and then we take in the struct key tab array. So that's effectively a pointer. And then we have the number of elements of the array. And bin search is not recursive. I thought maybe it would be recursive given the last argument, but it's not. It's iterative here. I prefer a recursive implementation just because it's easier for me to understand. But basically we go in, we say, hey, the low value is 0. The high value is the end. So we're setting our little indices at the beginning and end of the array. And we say while low is less than high, that means that we have searching to do. If it's equal high, that means that we found our element. If it's exceeded high, then it also means that we found the element and we need or the element doesn't exist at that point. Okay, so then low plus high divided by 2. So we take in the midpoint between the low and high. And then we say, hey, take that element, grab its word, compare that to the word that we were passed in our argument. And if that is less than 0, that means that we're on the left-hand side. We're not on the right-hand side. So then our high we set to mid minus 1. We don't set it to mid because we've already checked mid. So we can set it mid minus 1. Else if condition is greater than 0, then we do the inverse where we move the low indice up to mid plus 1. And then if it came back and the condition was equal to both, then we just return mid because we found it. And if we do that enough, eventually the indices will move past each other and will return -1 as a no result. And then if we look back at our binary search, we have the, hey, is bin search greater than or equal to 0? In which case we found it. If it's negative, it's that little condition there. That means that our -1 error is handled correctly. Cool. So we will show the function getWord in a moment. So yeah, the getWord was not provided yet. It's for declared. For now, it suffices to say that each call to getWord finds a word, which is copied into an array named as its first argument. The quality and keys is a number of keywords in key tab. Although we could count this by hand, it's a lot easier and safer to do this by machine, especially if the list is subject to change. One possibility would be to terminate the list of initializers with a null pointer and then loop along key tab until the end is found. But this is more than is needed since the size of the array is completely determined at compile time. The size of the array is the size of one entry times the number of entries. So the number of entries is just the size of the whole table divided by the size of the element of the table. That'll give you how many elements are in there. C provides a compile time unary operator called size of that can be used. So this is important. C provides a compile time unary operator. And I learned this the other day that size of is an operator. When you read it in code, it looks like it's usually with the parentheses around the operand. And so it kind of looks like a function invocation. But size of is indeed a operator. It's a unary operator. It's not a function. And it's entirely compile time. So C provides a compile time unary operator called size of that can be used to compute the size of an object. The expression size of object and size of type name. So when you give it a type, I guess you need to use the parentheses. Whereas the object, you don't need to give it the parentheses. Okay. Yield an integer equal to the size of the specific object or type in bytes. Strictly, size of produces an unsigned integer value whose type size t is defined in the header standard def.h. An object can be a variable or an array or structure. A type can be the name of a basic type like int or double, or a derived type like a structure or a pointer. So I guess the thing to keep in mind here, oops, go back here. I'm gonna hit Control-0 to zoom in there. Let's go ahead and just blow this away. So we're gonna do our main here, and we're just gonna say printf, and we could do something like %. I think I gotta do LD here for the size of. I think it's a long size of foo, and actually, you know what? We'll do an int, and here we'll just say, hey, size of int is equal to that foo and foo, and here we'll say what do you want to do? Uint 64t foo is equal to 12. 1, 2, 3. Yeah, that's fine. And up here, I think I need pound include standard int.h. I think that's it. Printf, of course, I need standard IO. And then standard lib for the little fancy access. Okay. Bam. All right. So here we can say make. Let's mkdir chapter 6 mv test.c into chapter 6 size of test size of dot c, and we'll also cp chapter 04, and then here I want the make file and the dot get ignore, send that into chapter 06 is what I wanted. Yeah, 06. So I'm going to go from 05 to 06, and then we'll just cd into that right there. All right, so now I can make and run get status, get at all, get status, build that thing. Okay, size of int and size of foo. Both of them work with parentheses around them. But let's test it without the parentheses. So I'll do them without. There we go. So that does not work. Expected parentheses on type name of, let's do that. Expected parentheses around type name in size of expression fix available. So we'll just say this is, we'll just say invalid and maybe we'll just do like this. Expected expression. Why do you expect expression? Oh well, DT that. We'll say compiler error. And you know what? I'm going to grab this and then I'm going to undo everything we just did, because I want to see the actual compiler error. I want to have them prove it. Yeah, it's a error. So if I echo this, if I make clean and I make again and I echo my exit code, it's an error. And if I look under build, there's nothing there. So it's definitely a compiler error. So I just wanted to validate that myself. Make. So now if I run build this thing, so you could do size of as a, even though it's a unary operator, I think the types need to be in parentheses. Kind of like when you're casting, the type needs to be in parentheses. And that probably has to do something with the language grammar that I'm just not familiar with. But the important thing here to note is that size of is a unary operator. All right, let's go back to the text here. All right, where are we? I forget where we left off. We'll just read from this statement here. Size of type name yields an integer equal to the size of the specified object in bytes. Strictly, size of produces an unsigned integer value whose type, size t, is defined in the so-and-so header. An object can be a variable or an array or structure. The type name can be the name of the basic type like int or double, or a derived type like a structure or a pointer. In our case, the number of keywords is the size of the array divided by the size of one element. This computation is used in a pound define statement to set the values of n keys. Okay, and since this is all like determined at compile time, I think that this will just go like literally it'll resolve to a numerical value at compile time. Like you won't actually have to run any computation, like any division operation at runtime. Another way to write this is divide an array size by the size of the specific element. Yeah, that works too. I've seen both. This has the advantage that it does not need to change if the type changes. The size of a size of cannot be used in an if line, like a macro if, because the preprocessor does not parse type names. but the expression in the pound defined is not evaluated by the preprocessor, so the code here is legal. Now for the function getWord, we have written a more general getWord that is necessary for this program, but it is not complicated. GetWord fetches the next word from the input, where a word is either a string of letters and digits beginning with a letter. It's either a string of letters and digits beginning with a letter, or a single non-white space character. The function value is the first character of the word. Or EOF for end of file, or a character itself if it's not alphabetic. Okay, so going to the next one here, get word. So this is just a fragment of the program. Let's go ahead and read this. So we say, hey, get word or character from input. So you say get word, you give it the buffer to write into and the limit on the buffer. Then we just do a forward declaration of get, unget ch and get ch. These are previously implemented functions in the text. We say, hey, get this character. If it's a space, we're just going to continue iterating. We're not going to process that. And then we say, if this character is not equal to EOF, then this word pointer, we increment. Sorry, we set the word pointer, the array, we assign the character into the array, and then we increment the counter. We increment the pointer, I should say. So just to clarify here, what's happening is when we entered this function, we did some declarations on this get ch, unget ch functions, and the C variable, which is where we're going to store our character. But then we also took this array. It's a char star here, but it's effectively an array, and we assigned it into char star W. And I imagine that's because we're going to be doing pointer arithmetic and mutations on the W, but we want to keep the original value for referencing it later, which is exactly what happens here. So this first section, we just enter our while loop. We say, okay, is it a space? Then we're just going to continue. So that by the time we get down to here, we know that we have a character assigned to C that's not a space character. And if it's not equal to EOF, then what we do, because this is a post increment on the W, that means that it happens after the value is used in the expression. So this expression evaluates to the current value stored at W. So we assign C into the current value at the W pointer. And then we increment it by one element. Because it's a char star, that'd be incrementing it by 1 byte. And then we say, hey, is that alpha? Is that an alpha character? If it's not, then we're done. And we're going to say, hey, that you added the C. Now we're going to add the null byte, and we're going to return C itself, which is the last character that was read by getch. And then you could see, oh, interesting. Okay, it's not what I thought would happen here. So then we go into a for loop. The for loop has no initializer. Every time we complete the for loop, we're going to advance the pointer into W, into the array. So we have the original pointer, which is word, and then W starts at the same location as word, and it gets advanced not only from this initial write, but also here. And what we're doing here is we're calling getch. We're writing additional word. Basically, all of this code up here is to get us to a place where we have a first character that is an alpha character. And then after that, it's less strict about what it is. So here, we get our character, we immediately sign it into where word is pointed at, and then we return that value. And they say if it's not alphanumerical, then we unget that value. It's still in the array, but we're going to break out of the loop and overwrite it with a null byte. So this allows us to consume all of those alpha characters. We're doing get ch, as long as it's not an alpha, as long as it's an alphanumerical character. This is alpha num. This was just alpha up here. So as long as this is an alphanumerical character, then we're going to continue writing into the buffer up to the limit. That's why the limit condition is here. So the limit is being decremented each time we assign into it, which allows us to make sure that we have space in the buffer to write it. And then finally, we add that null terminating byte when there is a non-alphanumerical character, in which case it gets added back to the buffer, or back to the buffer that is used for getting characters, or we hit the limit, in which case we want to just throw a 0 there. So I think there is a possibility here that we lose a character. I think there might be a bug here where we hit the limit and then this is going to clobber. No, because we advanced the word here. So this will not be clobbering that. Okay, so there's no bug here. And at the very end, we just return the 0th element, which is a copy of the character that was at the initial 0th element. It's the same thing that we would have returned up here. Yeah, I believe we could have just used C. No, because yeah, I think we could have used C instead of word 0, but it's fine. Okay, so let's read through the text here. Get word uses get character and unget character that we wrote in chapter 4. When the collection of an alphanumerical token stops, get word has gone one character too far. Yeah. We call get uncharacter, pushes that character back into the input for the next call. Get word also uses is space to skip white space, is alpha for identifying letters, and is al num to identify letters and digits. All are from the standard header ctype.h. Exercise 6.1. Our version of get word does not properly handle underscores, strings, constants, comments, or preprocessor control lines. Write a better version. Nah, I'm good. Okay, pointers to structures. To illustrate some of the considerations involved with pointers to arrays of structures, involved with pointers to and arrays of structures, let us write a keyword counting program again, this time using pointers instead of array indices. The external declaration of key tab need not change, but main and bin search do need modification. Okay. Let's go on to the next program here. So we still have the same prototypes, it looks like. Get word and bin search. Let's see, bin search previously was returning an integer, now it's returning a struct key pointer, but it still receives the same arguments. So this thing's returning a pointer now instead of an integer, which makes sense because the array, we're not using indices anymore. So here our bin search gives us P, which is the thing that we found, which makes a lot more sense than N. And then here we just increment the count. Totally makes sense. And then here we assign P to be the 0th element of the array. And then we say, hey, if it's less than key tab plus n keys. So key tab is the array. And then we say plus n keys. So this is point arithmetic as well. So we're saying offset by the number of elements. As long as P is less than that value, we're going to P plus plus it. And then if P count is greater than 0, then we print it out. So just slight difference in the implementation there. Then binary search here. So binary search, we accept the pointer to the 0th element of the array as tab. Then we say, hey, give me a reference to that 0th element, which I think you could have just assigned the tab itself. You could have copied tab into low, and I think that would have been the same thing as this. But then here's where the other bit goes here. So we say, which is interesting, bin search is passing at n keys. I would have thought that this would have been out of bounds, right? But maybe it's safe. I would have thought that we needed to go one shy of that. Because if you have 10 elements, 0, 1, let's say you have 2 elements. N is going to equal 2. Then you're going to use 2 as an indice into tab, which is going to go 1, 2, and it's going to be at a place where it's off the end. So high really isn't pointing at the element that's being considered, it's pointing one past it. So it's just important to keep in mind that this is high is not in a valid state here. And then mid, of course, is just a pointer. I would have preferred them to do n-1 here, to be honest. This is kind of a little bit scary. It depends how we're using high, though. We're assigning it to high potentially here. And we're saying, okay, low is less than high. Okay, it's still safe. Then we say high minus low divided by 2. That's still safe. Let's look at the other implementation. Yeah, so they said they did less than equals on the other implementation, whereas we're just doing less than here. And I think that really is the difference. Yeah. So I think this is safe. But walking through all that in my head is, I don't really have the brain power to like do all that. I would probably want to have some test cases to cover this and just write the tests, and show and have logging that shows like how the array is being accessed. But immediately this is kind of sus to me, because this high value here is pointing at the like beyond the actual bounds of the array. But as long as we don't actually reference anything there, I think we're good. So here we're doing divided by 2, so that's potentially going to be lower than the high value, so we're not worried there. And then we assign to the high pointer, but we don't assign to what it's referencing, so we're not dereferencing it yet. Okay, so say we had one element. Let's just say there's one element. Let's walk it through that example. I can do that in my head. So then tab 0 is pointing to this place, and then tab 1 is pointing one element over. Low is less than high. So the midpoint between low, so high minus low is going to give us the value 1. 1 divided by 2 is going to be 0. So low plus 0, so we'll be pointing at low. Mid will be low. So that's the other thing, is like we're always biased towards rounding down in these address space here because of the division by 2. Integer division, it rounds down. So technically, like in between the valid element and the invalid element, we're halfway between, but we round down. If we rounded up, we would be in a bad situation. Because integer division is going down, it'll put us on the right element. So it would be on mid, and then we compare that and say they don't match. Say there's no match. Then we would go down one of these branches here. So then mid would be high, or mid would be low. So there's two potentials. And this is going to be mid plus 1. Oh, interesting. Let's go down this branch. So the comparison came back where condition was greater than 0. So now we say, okay, mid plus 1. So now that low value is also, high and low are both invalid. But by the time we get up here, the comparison, they're actually equal. So both of them are invalid, but both of them are equal, so they fail this comparison check and return null. So that's safe. if you go down this branch, then high would be moved to mid, which means that they're both equal as well, so they'll fail the condition. I mean, they're both equal, but they're both valid, and they'll fail the condition, so that's fine. So in this one test case that I just ran through my head, it seems like that would be fine. But yeah, I would want a little bit more testing around like making sure that this is valid, because usually when you're referencing memory beyond the bounds of the array, it's something you should kind of like, you should consider having some extra testing around that, just to make sure you're not referencing invalid memory. Okay, so let's continue reading. There are several things worthy of note here. First, the declaration of bin search must indicate that it returns a pointer to the struct key instead of an integer. This is declared both in the function prototype and in bin search. If bin search finds the word, it returns a pointer to it. If it fails, it returns null. So anywhere that we're passing this reference back up the stack, anything up in the caller that uses that pointer needs to do a null check, because it might get a null value out. Let's see here. Second, the elements of key tab are now accessed by pointers. Boop. This requires significant changes to bin search. The initializers for low and high are now pointers to the beginning and just past the end of the table. The computation of the middle element can no longer be simply low plus I divided by 2, because the additional, okay, so that was something that is low plus, yeah, because the pointers, okay, that makes sense. Computation of the middle element cannot simply be this expression, because the addition of 2 pointers is illegal. Subtraction is legal, however, so high minus low is the number of elements, and thus low plus high minus low divided by 2 sets a midpoint to the element halfway between low and high. The most important change is to adjust the algorithm to make sure that it does not generate an illegal pointer or attempt to access an element outside of the array. The problem is that tab -1 and tab n are both outside the limits of the array tab. The former is strictly illegal, and it is illegal to dereference the latter. So the former would be illegal. So the compiler would find, no, the compiler can't find that, because the -1 would be determined at runtime. So I guess let's go ahead and see what happens there. Vim test illegal array bounds access .c. I'm just gonna read in the other test that we did, because I don't want to like repeat a bunch of this stuff. So say we have a array, we'll call it the integer array foo, and it's gonna have 2 elements, and we'll just do, actually, let me grab this declaration. I'm gonna initialize it to 0, because why not? But we're gonna undo all this because I want my printfs back, and then I'm just gonna delete some of these. Oops. And what do we want to print out here? The different elements. So we're gonna say foo sub 0, and we could just do D here. I don't think it needs to be LD. And then we'll do a foo sub 0, my favorite character in Mortal Kombat. And then we're gonna have foo 1, which should be totally valid. And then this is where we get invalid, because we're going off the end of the bounds. And then foo -1. -1. And I think this will be a compiler error, because it can be determined at compile time. But let's see. Make. No, it was not a compiler error. Echo says everything's happy. Build test illegal. Okay. So 2 we access beyond there. Some random value. What's amazing is that foo -1 let's actually declare here an int don't access is equal to what do we want to call this? 99999. Why not? It might like okay. It didn't get it at the end of the array because it probably optimized that thing away. Let's do 88888 and then 9999. Boom, 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 boom. Okay, so we same result. Where the end of the array is completely invalid. So what I'm going to do here is I'm also going to assign after these statements, I'm going to assign into a global int keep around. Just to keep it around. We'll call this keep from optimizing. Keep from optimizing. What this will do is if we assign into keep from optimizing, because these values are being, why is that not complete? Because these values are being assigned into global memory at a later time, the optimizer can't just like throw them away. At least that's my intuition here. I don't know that for a fact, but we'll test it and see what happens. There we go. Make. Okay, so foo2, we still do not get the value we expected. That is interesting. I would have expected it to be packed like this, the way it's declared. But it does not appear to be that. We could disassemble it to see why. I'm gonna try doing that. It's been a while since I've done a disassembly here. So obj dump, man obj dump. I think that's S. Disassembly D. Disassemble main. So I'm gonna say obj dump. Obj dump. Disassemble main, and we're gonna give it the binary. Test illegal. Yeah, let's do that. Okay, so here's main here. These are all our calls to printf. Oh god, I just had this feeling of like, oh, now I'm gonna have to do more math in my head to figure out where this stuff is located at. All right. So RSP is our stack pointer. And RBP is the base pointer of the stack frame. So stack pointer is the pointer to the place on the stack of the current element of the stack. And then base pointer is the location where the base of the stack frame is, I believe. If we pull up a diagram here, I'm just going to Google image search for RBP versus RSP, and we're going to go to images. And I'm going to find one that is nice. Here we go. So we got our base pointer and our stack pointer. You can see how it's pointing past. I think it should point past the element. It's not a great illustration. Here we go. This one's better. Oh, that's the actual YouTube video. Don't really want to watch YouTube video. But if you see here, the RBP, what's really weird is he used the same address here, which makes it even more confusing. So that's not a great image either. Maybe this one? How is there not like a decent image? I just want an image of like where the RBP and RSP are on the stack. This guy maybe? This guy. So this is going from low address to high address. So you basically have to invert it in your head. Because the stack will, in this case, will be growing upwards. And normally it's, in my mind, I like to view it stack growing downwards because it's going from high to low. High addresses should be high on the screen and low addresses should be low on the screen. But in this diagram, it's inverted. So RSP is the stack pointer. Yeah, okay. I keep on having to mentally revert it in my head. So the base pointer is pointing to the stack frame, and the stack pointer, like I said, is pointing to the current element in the stack. And let's just confirm that with ChatGPT. Very briefly describe the difference between RSP and RBP, assuming I already know about the stack and registers. Be super terse in your response. I just want to confirm this. Yeah, exactly. Okay, so we say, hey, the current stack frame, which when we entered the main is actually pointing to the previous stack frame, not this new stack frame. So we got to set up our stack frame. So we push the previous base pointer onto the stack. And then we say, hey, move the RBP value. Wait a minute. Is this left to right or right to left? Is objdumps disassembler for AMD 64 assigning values right to left or left to right? Forget. The default output format instruction source destination. Okay. Okay, so then we take the current stack pointer. So this is pointing beyond where we just wrote the base pointer. This is all preamble stuff, by the way. I'm just refreshing my neurons for it because I want to get more into assembly. So we're saying, hey, take the stack pointer value, which is currently pointing to the place that we stored base pointer, and then we're gonna, or the next element up from that, and we're gonna assign that into the base pointer. So we just saved off the previous base pointer for the previous stack frame, put it in our own base pointer. So it's left to right, so we're assigning into the right hand side. So we say, hey, take the value 30. So if we bring up our code here, vim test illegal. You know, it'd be really good at just putting this into Godbolt. Because it actually does the mapping of things a little bit easier. I'm gonna do C here. Square. You're a square. Okay. Can you not do that? Okay. Here we go. Okay, here we go. So this is all preamble. And so now it's flipped. So we're doing the reverse of what I was just looking at. So this syntax is right to left. So we're signing into the left-hand side. So we take our stack pointer, like we said, put it, wait a minute, is it reversed? Stack pointer, base pointer, yeah. So here we're taking our stack pointer, we're assigning it to the new base pointer. Okay, so this is all to set up the, save and set up the new base pointer. And then we subtract 32 from the stack pointer. I wonder why we do that. So this is all preamble. So they're probably going to write some stuff into here. Yeah, base pointer minus 22. We store RSI and EDI. So this is probably to store arguments. So this is going to be our argc and our argv. So in the case of integer, on 64-bit AMD, an integer is 4 bytes. So let's ask AI. On AMD 64, 1 second. All right. So on AMD 64, what are ABI? Say ABI. What are EDI and RSI registers used for in the function preamble? Yeah, okay. I just called it preamble because I thought dealing with function arguments would be preamble-ish. So that means when we're calling into this function, we set EDI and RSI to those registers to, or I guess RDI and RSI to these values. Oh, and we're going to store a bunch of like... So all these values here, along with the arguments, are being stored into the stack here. So that's why I advanced the stack pointer by 32. We could have done the advancement of the stack pointer by 32 after all of this, because they're not using push or pop instructions. So I think it would have been an equivalent. I don't know why they do it first. Maybe because, to be honest, I have no idea. I would just be guessing. But what's interesting is that integer on AMD 64, I believe, is a 4-byte value. So you can see that's why they said, okay, take the base pointer minus 4, because we already stored, wait a minute. The base pointer here, okay, we're saying base pointer minus 4, store the 4-byte value here. Then we have this 2 element. So this is going to be an 8-byte wide array. Hold on, give me 1 second. I heard someone outside. I had to check to make sure there wasn't anyone outside here. All right. I'm going to put a bookmark in our little test location there. Okay. So we're going through the initialization of the local variables on the stack here. The first value, like in memory, I guess. So the first value in memory is this one here, which again is 4 bytes. And then what I was saying before is that integer array of 2 bytes is going to be, or sorry, of 2 elements is going to be 8 bytes total. So you might be thinking like, oh, why did they put it at -16? It's because this one went next. So basically, these two values get put on the stack in order. Then the array gets put on the stack. Then our arguments get put on the stack. So we're already at, let's see, 4 bytes, 8 bytes. Because the memory gets written from lower up higher, so I'm getting used to the stack stuff. So I spent a little bit of time like reading disassembly and like, but it's mostly like I was doing my own assembly programming, and so I was able to kind of like, you know, do my own stuff. And this isn't the way that I would have done this. So this is my first time kind of like looking at the output of the compiler, looking at the stack and trying to reverse engineer like what it's doing. So when you go -4, it then writes up to the value. Instead of going from -4 to -8, it goes from -4 to 0, effectively. -4 to 1, I guess, because -4, -3, -2, -1. So you'd have those 4 bytes that would be written to. Okay, so -4, -8, -16. And then we have 20 here, so our integer argc is going there. And then this 32 is interesting. So that means that we have 12 bytes set aside for argv. That seems weird to me. RSI is the second argument, but why would it go ahead 12 bytes? My guess is to make sure that it's aligned on a specific the pointer is aligned on a specific boundary, maybe. But it's not going to use all those 12 bytes. On this machine, a 64-bit machine, it only needs 8 bytes. So that means there's 4 bytes being wasted there. And my guess is to get it to a proper alignment. So I think at this point we're at like a proper alignment. In case we want to do potentially like, I don't know. To be honest, the only time I've run into alignment issues is on atomics, where the CPU needs the memory to be on a specific, alignment, specific 32 or 64-bit alignment. And yeah, I guess this is probably for alignment. They waste 4 bytes here for alignment, probably. Okay, so now here, this is all printf stuff. I love this compiler explorer. So you can see here, we're taking the dword pointer. So there's all these strings. So these are just like memory addresses where these things are located at. But we're saying, hey, take the RBP -16, which we determined is that initial element of the array. We're saying, hey, take that dword pointer and store it into EAX. So we want the value here. So I think this bracket notation is like pointer arithmetic. And then this is kind of like a dereferencing, like asterisk and C. I think that's what that means, the brackets. So this is saying, hey, take the base pointer -16, which is where we stored the value. This is like actually get that value. This is a dereferencing. I think that's just typing to say how much of this that we want to dereference and store into EAX. But EAX will give us the size. dword would be 32, and then EAX, because it's a 32-bit register, will give us the 32. So let's just say, hey, let's ask AI here. In this instruction, what does dword PTR mean? I know it means like 32-bit pointer, but yeah, 32-bit. The 4 bytes stored at memory address, so and so. Yeah, the assembly needs to know, are we loading 1 byte, 2 bytes, 4 bytes? Okay, so that means the read side needs to know how many bytes to read. Even though the destination is 32-bit, you might want to only read like 1 byte and then store 1 byte in the low order bits, you know. So you do need to specify how many bits you're going to read and how many you're going to write by using the right register size. Okay, so that makes sense. Okay, so then we say, hey, EAX, ESI. So ESI, I need to pull back up AI and see, give me that table again, because I need to know what ESI is. Oops. Is a second argument. There is no second argument. So I'm not sure why it copied it again into ESI. EDI would be the first argument. What is EA? I thought EAX was the... Oh, EAX, we assign 0 into EAX. So this is clearly like unoptimized code here, because I don't think it would have done all this in an optimized program. But if we look, it's setting 0 to EAX. So I think it's using EAX as just like a temporary location to store this value. So we read the value, we then write it to ESI, which is a second argument, which it is a second argument in printf. And then EDI, which would be the first argument. Does this thing know that it's 64-bit? Because it looks like it's 32-bit. C x86-64. Okay, well, it's using a mixture of 32 and 64-bit registers here. Maybe it's using the 32-bit registers just because it can, because the values are not big enough. I would think that the EDI here, E is 32-bit. I would think that this string would need a 64-bit pointer, right? Okay. I'm a bit confused why it can use a 32-bit value here. But it's doing the same thing for all these. Where it just computes offsets. So 16 and 12 are valid offsets into this base pointer. -8 is not. That's where we stored 99. 20 is where we stored... Oh, interesting. It's because the ordering here is not the same as the ordering here. So if we look, -8, that's why we saw a 9 come out. But then 20, which is beyond the end of the array, -16, -12, those are all valid. -8 will give us the 9. Oh, interesting. What happened when we ran this? Did we see the 9s come out? Yeah. And that was -1. So we went here down to here. So if we want to actually get to the 8s, we need to continue going down. So we need to go -2 here. So that explains that. And then I don't need these. I don't think I need these. Okay, so that explains why we see what we see, is that when it was storing these fields, it stored them in different locations in the stack than the order that we see here. So 8 was -4, -4, -8, and then so it went here, then here, then here. So I'm gonna ask, is there a way in C to have the compiler store local variables on the stack in the order in which they are declared, and not have the compiler reorder things? Short answer, no. The C standard does not guarantee any ordering of local automatic variables on the stack, and there's no portable way to force it. Now let's unpack what is really going on. The standard's position for local variables. What you can control, yeah, just put them in a struct. I was gonna say, because I know structs are guaranteed. Volatile does not help. Prevents certain optimizations, but does not guarantee stack placement. Care about layout, you actually want a struct. Oh, so you can just allocate an array on the stack, and then you can pull pointers off of that for your values. That works too. That's interesting. Locals are abstract storage with automatic duration. Their physical placement is an implementation detail. But if we wanted to read the right value, so now that we've understood what's going on here, I'm going to go ahead and pull up our code. That is old. Let's go ahead. Jobs? Do I have any more jobs? Jesus Christ, I have so many jobs. Okay. Test illegal. And we're going to go -2. Oops, -2. And then I'm going to delete all this stuff. Make, build, test, illegal array access. There's our 8s. So you can see kind of it reordered things on the stack. For whatever reason, it wasted 4 bytes for some alignment purpose probably. And then there's 2 solutions that I came up with that the AI recommended. One of them I thought of, which is to use a struct to ensure that the ordering is the way that you expect it. The other is just to put an array on the stack and get pointers to it. And, you know, it's not going to reorder bytes inside of your array. Your array is guaranteed to be a contiguous piece of memory. So, cool. All right, let's get back to reading the book now that we had that little side quest. Okay. So, we left off around here, where it basically said the former is strictly illegal, and it is illegal to dereference the latter. But we were able to do both of those. We weren't able to get a reference to it. I don't know. That seems weird. Let's maybe go in here. And here's where they said that this is illegal. The former is illegal. This is already dereferenced. Yeah, C doesn't care. It's like, gonna do it anyways. Not gonna let you know that it's illegal. Yeah, I was just kind of confused about the phrasing of illegal. Usually something that's illegal means that you can't do it. But in C's more like You know how the government like allows you to break laws, even if it's illegal to do so, and then punishes you after the fact? That's kind of like what C does here. It allows you to break their laws, and you just have to pay the consequences. Okay, the former is strictly legal and is legal to dereference the latter. The language definition does guarantee, however, that pointer arithmetic that involves the first element beyond the end of the array, that is tab n, will work correctly. Oh, that's right. They mentioned that before, that you can use pointer arithmetic one element beyond the array, and that's probably to make algorithms easier to implement. In the main, we wrote p key tab is less than p key tab plus n keys plus p plus plus. If p is a pointer to a structure, arithmetic on p takes into account the size of the structure. So p plus plus increments p by the correct amount to get the next element of the array of structures, and the last test stops the loop at the right time. Don't assume, however, that the size of a structure is the sum of the sizes of its members because of alignment. Literally, that's literally the next word is because of alignment requirements for different objects. There may be unnamed holes in a structure. Thus, for instance, if a char is 1 byte and an int is 4 bytes, the structure char int might be 8 bytes. Might well require 8 bytes, not 5. The size of operator returns the proper value. Finally, an aside on program format: when a function returns a complicated type, like a structure pointer, as in struct key star bin search so-and-so, the function name can be hard to see and to find with a text editor. Accordingly, an alternative style is sometimes use struct key star and then the name. This is a matter of personal taste. Pick from the form you like and hold to it. Boop. Self-referential structures. Okay. I felt that was a productive little section on structures. How many more pages do we got on structures? We got a lot here. We got 1, 2. Oh, I'll just count them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 12 more pages on this chapter. All right. Self-referential structures. Suppose we want to handle the more general problem of counting the occurrences of all the words in some input. All the words in some input, okay? Since a list of words isn't known in advance, we can't conveniently sort it into and use a binary search. Yet we can't do a linear search for each word as it arrives. To see if it's already been seen, the program would take too long. So, I mean, the way that you would solve this nowadays is just to use a table doubling hash map, where you just read a word, put it in the hash map, increment the counter, keep on doing that. The data structure is going to reallocate and table double as it gets filled. You can even pre-allocate it if you have an idea of how big it's going to be. And then once you're done, you can do whatever you want with that data structure. Okay, so it said here, yet we can't do a linear search for each word as it arrives to see if it's already been seen. The program would take too long. More precisely, its runtime is likely to grow quadratic with the number of input words. How can we organize the data to cope efficiently with the list of arbitrary words? One solution is to keep a set of words seen so far sorted at all times. By placing each word into its proper position in the order as it arrives, this shouldn't be done by shifting words in a linear array, though that also takes too long. Instead, we will use a data structure called a binary tree containing one node per distinct word. Each node contains a pointer to the next word, a pointer to the text of the word, a count on the number of occurrences, pointer to the left child, and a pointer to the right child. Simple binary tree. And they can use binary search to find the node. No node may have more than 2 children. It might have only 0 or 1. The nodes are maintained so that any node in the left subtree contains only words that are lexicographically less than the word at the node, and the right subtree contains only words that are greater. This is the tree for the sentence, "Now is the time for all good men to come to the aid of their party," as built by inserting each word as it is encountered. To find out whether a new word is already in the tree, start at the root. So, some questions around algorithmic complexity with this data structure. So, insertion is going to require a binary search to find the place to insert. Once you found the location to insert, the insertion is O of 1. But the binary search is O of n, O of log n, depending on the balancing of the tree. If it's a linked list, then it's going to be O of n. Worst case, O of n. But an average case would be log n. So that would be for insertion. Practically, for insertion, you're going to take O of log n. And then for reading, checking membership and reading its value, that's going to be O of log n as well. What are the type of access patterns that we're going to have here? So we're going to be counting all of the words that may occur. So it's going to be a lot of like reading a word, checking its membership, and once we found the place in the tree that we want to operate on, then we would either do an insertion or do just an increment on the counter that's attached to that node. So that's going to be the primary access pattern: is search, insert, search, increment, search, insert, search, increment. So it's O of log n for every element, every word that we're reading. And at the end, we want to just dump the entire tree. So that's going to be O of n, basically. I believe to traverse, yeah, it would just be a recursive O of n. But if you want to traverse it in order, then you'd have to go all the way down the tree, and then you'd have to like work your way back. So I think a general traversal, you're looking at O of n. A ordered traversal, probably going to be more costly. But either way, the insertion cost being over log n is too high compared to a hash map where it's O of 1 to do the insertions and increments that you're looking to do in this program. So hash map would just be the way to solve this. You wouldn't use a binary tree for this. All right. Let's continue reading. No nodes may have more than two children. It might have only 0 or 1. The nodes are maintained so that at any node, the left subtree only contains words that are lexicographically less than the word at the node, and the right subtree only words that are greater. This is the tree for the sentence, as built by inserting each word as is encountered. To find out whether a new word is already in the tree, start at the root and compare the new word to the word stored at that node. If they match, the question is answered affirmatively. If the new word is less than the tree word, continue searching to left child, otherwise at the right child. If there is no child in the required direction, then a new word is not in the tree. And in fact, the empty slot is the proper place to add the new word. This process is recursive since the search from any node uses a search from one of its children. Accordingly, recursive routines for insertion and printing will be most natural. Going back to the description of a node, it is conversely represented as a structure with 4 components. So this is basic CS binary trees. So we got our T node, we got char star for our word, we got our count, we got our left and right nodes. This recursive declaration of a node. Oh yeah, because they got the T node defined recursively. Might look chancy, but it's correct. It is illegal for a structure to contain an instance of itself, but a pointer to an element of the same type is allowed. So-and-so declares left to be a pointer to T-node, not a T-node itself. Occasionally, one needs a variation of self-referential structures, two structures that refer to each other. The way to handle this is struct T has a pointer to S, and struct S has a pointer to T. The code for the whole program is surprisingly small given the handful of supporting routines like getWord that we've already written. The main routine reads words with getWord and installs them into tree with addTree. So we have our struct node, which is a root. So we're going to do malloc here, right? Let me look ahead here. Yeah, there's a talloc. So we're going to do allocations here. I mean, any type of pointer-based list or tree is going to use heap memory. All right, so we allocate on the stack a pointer to a root node. So we don't even have the root node. And then we have our buffer for our word that we're going to read into. And then we say, hey, the root, we're just going to set to null. I mean, they could have done that in one spot here. They didn't have to do it in separate lines. Well, get word. So we're going to say, hey, read into the word. Well, it's not EOF, and it's alpha. Word 0 is an alpha. Then we're going to add to the tree root, which is in this case null right now, the word. And then assign that back into the root. So the root might change as a result of adding elements to it. And then we're going to print the tree out using the tree print function, which should be fun. The function addTree is recursive. Oops, I'm on the wrong page here. The function addTree is recursive. A word is presented by main to the top level of the root of the tree. At each stage, that word is compared to the word already stored at the node and is percolated down to either the left or right subtrees by recursive calls to addTree. Eventually, the word either matches something already in the tree, in which case the count is incremented, or a null pointer is encountered, indicating a node must be created and added to the tree. If the new node is created, addTree returns a pointer to it, which is installed in the parent node. So here's the implementation of addTree. So you get a node P and the character pointer that we're going to add. So we say if P is null, then okay, we're at the point where we need to allocate because node's null. So we're going to make our node assign it into P. So P is just a stack pointer. It's a pointer that's stored on the stack. So we're just going to allocate up our node. We're going to duplicate the word because we need our own memory for the word. So it'd be nice if talloc did that for us because, yeah, we don't want more fragmentation of the memory than is necessary. We want all that, the allocation for the structure of the node and the data for the node should be in the same locality. Typically, that's a good idea. Having it somewhere else off in memory, you're going to be jumping around and having having cache line misses when you're doing your memory operations. But we do a stirred up here, which should be fine, I guess. Then we set our count to 1, and then we say, hey, your left and your right are both going to be null. We don't know what they're going to be yet. And then at the end, we just return it. Otherwise, so that's a condition where it's a new node. So our root getting past a null, that's what's going to happen. But now we might also be in like a subtree. So we say else, that means it's not null, if our word matches the word at the node, then we're just going to increment its count. And if it doesn't, then we're going to say, hey, add tree on the left-hand side. Go ahead and add tree, and we're going to assign that back to our left. And then same thing with the right. We say, hey, add tree. Here's the right node that I currently have. Either update it, continue traversing, or give me back a new node and I'll assign it into my right. So in all these cases, P is not mutated at all. The only time you mutate P is when it's a new node, when it's null. So that return P only has an effect when P is equal to null. So we're never going to use it to like swap out subtrees or anything. Okay. Storage for the new node is fetched by a routine talloc, which returns a pointer to a free space suitable for holding a tree node, and the new word is copied to a hidden place in stirdup. Hidden place by stirdup. We'll discuss these routines in a moment. The count is initialized, and the two children are made null. This part of the code is executed only at the leaves of the tree when a new node is being added. We have unwisely omitted error checking on the values returned by stirdup and talloc, just for brevity, I guess. Tree print prints the tree in sorted order. At each node, it prints the left subtree, all the words less than the word, and then prints the word itself, and then prints the right subtree. Feel shaky about how recursion works. Simulate tree print as it operates on the tree shown above. Okay, tree prints. You just give it a node to print, a root node. And then to say if you're null, we're not going to do anything. Otherwise, we're going to just tree print the left, and then we'll print out the node that you gave us, and then tree print the right. So that gives you an in-order printing. The problem is that the structure, it's just going to be all the values in a table. It doesn't show you the structure of the values, which I guess the structure isn't super important for this application. So that's one problem. And it's going to be O of n to print it. Because yeah, there's n nodes, and you're not going to spend any more time than that. Okay, practical note: if the tree becomes unbalanced because the words don't arrive in random order, the running time of the program can grow too much. As a worst case, if the words are already in order, this program does an expensive simulation of linear search. There are generalizations of the binary tree that do not suffer from this worst case behavior, but we will not describe them here. Before we leave this example, it is also worth a brief digression on a problem related to storage allocators. Clearly, it's desirable that there be only one storage allocator in a program, unless you're Zig, even though it allocates different kinds of objects. But if one allocator is to process requests for, say, pointers to chars and pointers to struct T nodes, two questions arise. First, how does it meet the requirement for most real machines that objects of certain types must satisfy alignment restrictions? For example, integers often must be located at even addresses. Second, what declarations can cope with the fact that an allocator must be necessarily return different kinds of pointers? Alignment requirements can generally be satisfied easily at the cost of some wasted space by ensuring that the allocator always returns a pointer that meets all alignment restrictions. The alloc of chapter 5 does not guarantee any particular alignment, so we use the standard library function malloc, which does. Chapter 8, we will show one way to implement malloc. The question of the type declaration for a function like malloc is a vexing one. It uses a void star. It's a vexing one for any language that takes its types checking seriously, which is not C. In C, the proper method is declare that malloc returns a pointer to void, then explicitly coerce the pointer into the desired type with a cast. Malloc and related routines are declared in the standard header standard lib.h. Thus, talloc can be written as malloc size of struct node, and then convert that into a struct node t node pointer before we return it. I wonder if you could just return. Let's do a little test program here. Vim test return. Return typed void star dot C. And I'm going to read in some of my other tests here because I don't want to deal with all this stuff. Okay, so we're just going to say printf, and we're going to give it the percent $t. Is that a type thing? And percent %v of the call to foo, and foo, we'll just say this is going to return an int star foo, and we'll malloc up size of int and return it without a cast. Or struct type. I'm going to convert this into a struct. So we say struct bar is maybe we would do like a, I don't know, what do you want to do here? Int x double y a char star z. Okay, size of is going to be bar, and this is going to return a pointer to bar. So I struct with a T, and I need my semicolon here, and then this thing, hey, struct tag to refer to type bar. Okay, I want to say struct bar, and then this has to be struct bar. There you go. And then we call foo here in value conversion v. Sorry, this needs to be p maybe. And how do you print out the type of a value in C with printf? I think it's because all type information is thrown away. Yeah. Okay, so we can't do that. But we'll just print out the pointer, why not? Oops. We know we get back the right type because, well, we do. Make. Actually, let me go up here. I don't think I need standard int. I do need these though. Okay. And before I move on, let me make sure that I don't think I need this guy, but I do need those. Okay. And then the original test size of, we do need that because we have uint64t here. Okay. And then we'll go up here, delete that. Test return. Okay, that looks good to me. Make. And then if we build test return, so it gives us back our pointer, no compiler errors. So it looks like maybe this, where is it down here? This explicit cast from malloc to the type that gets returned. I think that could just be handled implicitly. I mean, in Go, I would definitely say like, okay, you have to explicitly convert from one to the other. Otherwise, the compiler is just going to complain at you. But in C, I think it's fine. Stirdup merely copies the string given by its arguments into a safe place obtained by a call to malloc. So stirdup, we just do another malloc on the length of the string plus 1. Why do we do plus 1? Stirline is not going to give you the null byte as part of the length. And then we cast that to a char star, so our pointer is of the right type. I don't think you need to do that cast here because the type is already up here. And then we do a stir copy. Yep. But again, this is mallocing just some random place in memory. Really, you want those to be closer to each other. But it is what it is. Malloc returns null if no space is available. Stirdup passes that value on, leaving error handling to its caller. Storage obtained by calling malloc may be freed for reuse by calling free. See chapter 7-8. Write a program that reads a C program, prints it in alphabetical order each group of variable names that are identical in the first 6 characters but different somewhere thereafter. Don't count words within strings and comments. Make 6 a parameter that can be set from the command line. Don't care about that. Write a cross-referencer that prints a list of all words in a document, and for each word, a list of the line numbers in which it occurs. Remove noise words like the, and so on. Write a program that prints the distinct words in its input, sorted into descending order or frequency of occurrence. Precede each word by its count. Don't care about that. Okay, table lookup. So we got table lookup, type def, which I'm curious about, unions, bit fields. So one thing, explain struct tags in C with an example. Do so tersely. Do so briefly and without a lot of language. So that would be the tag. Okay, pretty self-explanatory. I always thought that when you do the type def, the second one, like the actual type def name was the tag, but I guess it's not that. It's the tag is the thing that the struct is actually named. All right, I'm gonna take a break here. Been going for a little over an hour. Learned a lot. We did some disassembly. We used Godbolt. Looked at how, we looked at function preamble, how C stores locals onto the stack, how it handles invalid memory accesses using an array syntax. Basically, it doesn't really complain about anything. And what else? Oh yeah, we went through the binary search algorithm and the data structure that they presented for binary search, which was pretty straightforward. We talked about the asymptotic complexity of that data structure, which isn't great for what we're trying to do here. And then, yeah, we just did a little bit of testing around how C behaves for returning a void star that you get from a call to malloc as a different type. And it seems like it handles it fine. Compiler doesn't complain at all. So, yeah, I'm going to take a break here, get some food in me, and then I'll hop on as soon as I'm done with that. And we'll jump into table lookups, and then type def, and then unions, and then bit fields. There's 4 more sections of this chapter, and then we're done with this chapter. Cool. All right. I'll be back in about 30 minutes. Not going to take too long here.